welcome back. So, let us recall till now what we have done regarding the convergence of the Fourier series. So, what we have seen is that first is that if f is twice continuously differentiable, then S n f converges to f, because this is going to be dominated f hat of n is of the order of 1 over n square. Hence, it is absolutely summable, and by the Fourier theorem we know that it converges to f. Next, what we have seen is that if f is continuous at some x naught, then we do not know whether the Fourier series is going to converge or not. However, we know that it is Cesaro summable. The partial sum, the Fourier series is Cesaro summable. In other words, f convolution of f n hat of x naught, this converges to f of x naught, and if f is belongs to c minus pi to pi continuous function, then convergence is uniform. Also, what we have seen is that for continuous function, the Fourier series is Abel summable. So, if f continuous at x naught, then f convolution of p, this is our a r f at x naught, this converges to f of x naught. If f belongs to c minus pi to pi, then uniform convergence. So, this is what we had observed about the convergence of the Fourier series. We do not know that whether this is going to converge or diverge for any continuous function. However, what we know is that if we have a continuous function, then the Fourier series converges in some other way, like it is Cesaro summable as well as it is Abel summable. Okay, so, now let us try to look at some applications of what we have done. Now, consider the steady state equation del u is equal to 0. Now, this is where the region what I am considering is the unit disk, and here all these are theta. So, I am looking for a solution in this region, and the boundary value is given to be u of, as you can see that u is a function of r and theta. So, u of 1 theta, this is equal to f of theta. So, this is our problem with the Dirichlet boundary condition. So, this is called Dirichlet problem. Now, if we want to solve, so recall that when we have started the Fourier series course, we got our inspiration from the steady state equation by taking the separation of variable and then proceeding, and we arrived at Fourier series. Now, and we didn't know at that point of time whether the solution what we are getting is unique or not. Now, let us try to solve this. Then I have the theorem, let f belongs to this is, let me take the Riemann integrable function on 0 to 2 pi, that means periodic and Riemann integrable. Define u of r theta, this is equal to f convolution of p r of theta. Then the following holds. What is? Then this particular u, we have del of u is equal to 0. Recall that delta, this operator, Laplacian operator in Cartesian coordinate is going to look like in R 2, and in polar coordinate this is del square by del r square plus 1 by r del by del r plus 1 by r square del square by del theta square. So, del u is equal to 0, b, theta is a point of continuity of f, then limit r goes to 1, I am coming from inside, 1 minus u of r theta, this is equal to f of theta. Now, in particular, if in the Dirichlet problem, if we were given with f a continuous function, 2 pi periodic continuous function, or rather this 2 pi periodic function, we can identify this on a function on a circle, then this f convolution p r theta, this is going to solve the Dirichlet problem in the disk. And moreover, the C is if f is continuous, then if f is continuous, then from B what we are going to get, limit r goes to 1 u r theta, this u r theta converges to f at the boundary r goes to 1 uniformly. So, if f is continuous, then u r theta is the unique solution to the steady state equation. Okay. So, now to prove this, we need to only prove A, because B already we have done, because u r theta is given to be f convolution of p r theta. So, we know that at the point of continuity this converges as r goes to 1. So, let us first prove A, then we will prove C. Okay. Proof. Now, we want to show delta u. Delta, let us recall, is del square by del r square plus 1 by r del by del r plus 1 by r square del square by del theta square. Okay. So, now we know that p r is a smooth function, therefore, f convolution p r is also going to be smooth. So, now if I want to get del square, so now let us calculate del square by del r square plus 1 by r del by del r plus 1 by r square del square by del theta square of the function p r theta So, this actually is n varies over z r to the power mod n e to the power I n theta. Now, this we are doing if I am taking delta of u, then we know that in the convolution I can shift the derivative to the function which is differentiable. That is the big advantage of the convolution. So, now let us do simply the taking the derivative. If I take the first derivative with respect to r, then I am going to get mod n times r to the power mod n minus of 1, and if I am going to take the second derivative, then the first term would be n mod n into mod n minus of 1 r to the power mod n minus 2 e to the power I n theta. Now, the second term, this is going to be, as you can see that for n equal to 0, this is 0, n equal to plus or minus 1, this is 0 2. So, this essentially this is mod n is greater or equal to 2. So, now this is the first derivative with the 1 by r, we have the first derivative is mod n r n minus of 1, then 1 by r is there. So, then this is e to the power I n theta, and the second derivative with respect to theta, r to the power n is not going to offer anything for us, it is independent of theta. Now, if I take first time the derivative, I will get minus I n e to the power I n theta, second derivative I will get I n square e to the power I n theta, then 1 by r square is here. So, we have r to the power n minus 2. So, now all these coefficients are same. So, as you can see that mod n mod into mod n is n square minus mod n, here it is a plus mod n. So, that gets cancelled, only we have n square. Now, here I square is minus 1. So, we have minus of n square. So, this is equal to 0, thus okay. Now, let us prove that the third part, which says that it is, if f is a continuous function, then this is going to be unique solution of the Dirichlet problem. So, when f is continuous, we have seen that f convolution of p r theta converges uniformly to f of theta as r goes to 1. So, that is what is very important for us. Now, let us show that whether it is unique. Let V r theta be another solution of the problem. That means what? That is just delta of V is equal to 0 and V of 1 theta with the abuse of notation. This is limit r goes to 1. So, this is f of theta. That is what is our solution. Now, let me, we want to show that V r theta should be equal to u r theta. Now, we know that if the Fourier coefficient of two functions, they are same and both of them are continuous function, then we have the uniqueness theorem tells us that f is equal to g. So, that is the approach what we are going to apply here. So, now let me define a n of r. This is equal to 1 by 2 pi minus pi to pi v r theta e to the power I n theta d theta. Now, this is given to us that delta v is equal to 0. Now, if I act this delta v, that means what I am going to get del square. So, we from this what we are going to get is that a n double prime of r plus 1 by r a n prime of r minus 1 by r square and then minus of n square by r square a n r. This is equal to 0. So, this will imply that a n of r, this is going to be equal to, the solution would be a n r to the power n plus b n r to the power minus of n. Now, we are looking for a bounded solution. So, n is positive, then b n is going to be equal to 0. Therefore, what we get is that a n of r is equal to a n r to the power n. Now, limit r goes to 1, if I take, then this is going to be, a n. Now, what is this? So, a n is equal to 1 by 2 pi minus pi to pi v r theta. As r goes to 1, it is nothing but f of theta and e to the power, I will put a minus sign over here, it is not minus of I n theta d theta. So, this is nothing but Fourier coefficient of n. Similarly, we can get for a negative, this is the Fourier coefficient, b n is going to be the Fourier coefficient of s. Therefore, thus the Fourier series of v r theta, this is equal to a summation over f hat of n, this is my a n, and then this is r to the power mod n e to the power I n theta. As we know that the u r theta also has the same Fourier series. Now, this is a continuous function. Therefore, what we are going to get is that both they are same, hence by uniqueness of Fourier transform, we have u is identically equal to v. So, that shows that is unique. I would like to make a remark that if f is continuous, then we are getting the u r theta f convolution of p r theta is a unique solution. That means, if the convergence is uniform, then we are getting it to be a unique solution. If the convergence is not uniform, then we have some problem. For example, we might have to compromise with the uniqueness. So, consider if convergence is not uniform, that means we are dropping that f is a continuous function on the boundary of the circle, then what we get is that define u of r theta, this is equal to del p r by del theta. Now, let us check, I apply the Laplacian with this. P r. Now, this is going to be when I am taking the derivative with respect to r twice, if I take, I will get mod n minus 1 r to the power n mod n minus 2, and then I have a factor of del by del theta. So, which is going to be I n e to the power I n theta. Similarly, if I do the second one, then this is going to be mod n r to the power mod n minus of 2, because 1 by r factor is there, and this is I n e to the power I n theta, and then the third one is going to be r to the power mod n minus 2 1 by r square, and then this is 3 times I am differentiating. So, this is I n into minus of n square and e to the power I n theta. Now, if we add all this, what we are going to get? This is 0. Now, what is the boundary value of this? So, now if we are looking at the boundary condition, then limit r goes to 1 minus del by del theta of p r, this is equal to 1 minus 2 r cos theta plus r square whole square, then this is minus of 1 minus of r square into this is minus minus plus. So, 2 r sin theta, and when r goes to 1, this is going to, we have already seen that this is equal to 0. However, so now here is this condition, this satisfies the differential equation, and limit r goes to 1, u of r theta, this is equal to 0. This satisfies this equation, because now we are not getting the uniform convergence here. If there is a uniform convergence, you would have got u identically equal to 0 is the solution of this differential equation. However, here we are finding that u is equal to del by del theta of p r, which is not identically equal to 0, but it is a solution of this differential equation. Hence, we cannot always talked about uniqueness. Okay, so this, that is why it is very important that when this is going to the convergence is uniform. I mean, to be more clear, so u is a solution, but and also v identically equal to 0 is also a solution. Hence, the uniqueness is broken. Okay, so this is one application of that what we have seen. So, now let us try to see that what happens. We are going to address basically now if f is not continuous, if f is continuous, what we have seen continuous at a point, then what we have seen is that the Fourier series is Abel summable to f at that point, and as well as Fourier series is Cesaro summable to f at that point. Now, it is natural to ask, suppose f is not continuous at a point, then what can we say about the convergence of Fourier series in terms of Abel summability and Cesaro summability? So, what we are going to address that if the nature of discontinuity is a very specific one, for example, if it is a jump discontinuity, then we can get something to work with. Okay, thank you.